Yeah, let me give the introduction first. Just wait. Yeah, today's that very happy for everyone to join our ASP seminar today. That today's that we are very happy to have Yifei Wang, yeah, a postdoc scholar that from MIT CCL to talk about two recent work. The first work is about is your next the first work is your next token prediction and transformers are best for it is for best for long context modeling. Yeah, let's welcome Yifei Wang. Yeah.
Okay, sure. Thanks, Cindy, for the introduction and for Sony also hosting me. So, thanks for coming. So today I'm going to talk about our recent work on kind of rethinking the two aspects of LMs, which is first nectar prediction is training objective, and transformer, which is the backbone networks. We know that. Okay, so LS is basically a combination of these two aspects, right? You have a very simple prediction objective that is just to predict next word. And you have a very powerful backbone network, which is transformer. And people that found that it also just go beyond just pure language. It can be anything. So you can do multimodal or any model modeling with this paradigm. So it's very powerful. I think it's gets us so far that we have not properly imagined like 3 years ago. I think it's also a great example of what Ilya called like minimal innovation and maximum results, right? Because it's very simple and you could just scale the performance. And we don't need more machine learning research. It's just kind of block our way to intelligence. Uh, and actually, if you look into many post-training methods we have today, like supervised fine-tuning or distillation or even RL, there are still simple variants of nectar prediction weighted by certain rewards to some extent. So it's still very generic and powers all the programs we have so far. But there's an overarching challenge. I think Ilya also himself also talked about this like probably last year that this not nectar prediction paradigm that we rely on in the past, I don't know, 3 or 5 years might have a diminishing return as the model scales larger and larger. I think that's actually, to be fair, makes sense because LMs are already fairly good at so many things. And every machine learning paradigm, right, it becomes so good, always have a kind of diminishing return. So it don't really surprise us, but the problem is we are still not there yet. We're still not that good on certain problems. And we might want to say how I can actually still try to bend the curve on remaining challenging tasks that we have today. So with this problem, actually, we might have to design some new algorithms, some variations of nectar prediction, or even something new. So this talk will basically talk these two aspects. In the first part, I will cover our actual work this year about what is wrong with nectar token prediction. Um, is entirely wrong, or is there something you can fix that actually makes it still works pretty well? The second thing is about transformers. We know transformers have uh, various position bias phenomena. There, where you put something in different locations, the context, even it's the exact the same thing, the performance actually varies a lot. So how does that really arise, and how to really understand that from a more rigorous and theoretic perspective, and how would that shed light on how we can design better methods? So that's the second part of this talk. So let's first look at the next token prediction. Um, so as we said, next prediction has done pretty good at many problems, but one of the remaining problems is actually how to scale this scheme to even longer context, because there are so many tasks that require us to understand a very long context. But the reason that current LLMs do not do that good on long context understanding is potentially because of the following reason that people observed from last year. That's your training objective, which is try to predict next token prediction better, give you a lower perplexity, right, which on the y-axis. And then people also care about certain long context benchmark scores, like how I can actually retrieve all my stuff from the context, so that people build kind of benchmarks on this. And the problem is that people observe that there's hardly any significant correlation between these two metrics. Like as we also replicate here, that you have a bunch of LMs, their perplexity scores don't really correlate well with their benchmark scores. That's a big problem. I think big problem on two aspects. The first is that we always try to use perplexity as like a de facto metric for evaluating language models, but it seems don't work on this long context language modeling anymore. So that's for evaluation. But I think a bigger problem is for training, because we are actually using next target prediction also for training. And for classical machine learning problems, the training and the evaluation are the same task. So the generalization is pretty easy given the models, have certain capability or localization. But now this figure basically suggests that there's no correlation between your training objective and your testing objective. Then meaning that your training is pretty ineffective in improving your generalization to the test metrics. Yep. Any questions? Okay, so I'll keep going. So I think that's the biggest thing in this long context understanding, and everybody is trying to figure it out. So for this evaluation problem, what people have to do so far is that because perplexity is not working anymore, so people just curate more and more benchmarks, try to cover all the aspects we care about long context understanding or training, like ruler, long eval, long bench, and there's more of them. But it's also very problematic because this is very much depend on some synthetic tasks like needle and haystack. It may not be really something we are using daily about long context understanding. Like you put some documents to GPT or something. So that's for evaluation. For the training, I think still the most effective way is just to feed the model with more data, hoping that the correlation can still bring you to the better generalization. And then you have to curate the data very carefully to have a very high quality long context data. So, but this two aspects, I think this have a similar spirit, right? That is just to introduce more and more human priors about what is the good data, what is good about long context understanding that we care about. But it's still human all to human, right? As nature said, I think this approach is not that what we ultimately want from this learning paradigm. And our intuition on this problem, because I work on satisfied learning, is that I still believe that maybe perplexity itself is still likelihood, right? It makes so much sense. So maybe it's still good enough for marrying long understanding, and we could possibly fix that. But we don't really know how to fix that. So actually answer this problem, we can actually take a look at how human benchmarks fix that. Like ask the question, when we really curate the data and benchmarks, what are we really curating from? So here is an example of a test case in the long eval benchmark, which is a typical, I think, like similar to needle and haystack thing, that you have a multiple K and query and K in the prompt, and your answer is trying to give the response given certain queries and retrieve the corresponding K that lies in a very long prompt. So this tests your long content understanding ability. I think the most important message from this is that we look at the response. Actually, there are many tokens in the response, but most of them are just not that long content relevant, and we only care about when we design the benchmark. We only care about the answer tokens, whether the model can score correctly on the answer tokens. So this benchmark is saying that some tokens in this long content understanding task is more critical than the others, and we should actually only focus on the accuracy of these tokens. Okay, so with this in mind, we actually design a proof of idea experiments by just calculating what happens with just calculating perplexity on these K tokens, because we would have that ground truth if we just do like a on like calculating some scores on the benchmarks, because guess benchmark, we know what is the K token, which is the answer token. You can extract that from the response. If you do that, you found that if you the probability on the answer tokens actually have beautiful correlation with this benchmark scores. I think it's kind of to be expected, but actually it really showed that it have a very strong significant correlation. But instead, if you calculate the probability on the non-answer token, that we have something very similar to what we see in the beginning, that there's no correlation. So actually, it's kind of suggests that the important, why perplexity is wrong is not because likelihood or log probability is anything wrong, but it's just because you're not computing that on the right tokens. And it's that simple. And why we actually need humans in curating all these benchmarks is that we just need humans to let us know what is important tokens that we care about in a task. And when designing synthetic tasks like a needle haystack, you would know what is token is wrong. But what you don't know is that if I gave you a natural corpus, like what is the K token in this natural corpus, that is unknown, that is unsurprised. So that is actually the only technical question left, that how we can identify the K tokens from a natural data without any human supervision, which is, I think, another satisfied learning problem. Like we don't have the ground truth or supervision about telling us what is the K tokens. And you cannot designing synthetic tasks to design this kind of supervision, but we also want to get this supervision just from the natural natural data. I think the last, but I think it's still something useful we learned from the previous, example of benchmarks, that when we evaluating long context, we are trying to find a token that really reflect the model's capability on long context, like the answer token. Whether you can answer the answer token correctly, reflect the models can understand in long context. And we can still observe very similar things in natural corpus. Like say you have a very long context, you have a sample in the beginning, sentence in the beginning, like Sarah have a dog named Buddy. Then after many talking, and you have to predict the following sentence that Sarah feels happy to play with Buddy. You can find that to predict the most of the tokens follow the word Sarah, you don't really need long context. It could just follow the previous tokens. But in order to play with the word body, because maybe the word body only appear once in the very beginning, then actually the word body is actually the key token here, because it actually requires the model to understand the key, the content in order to know the body, the word should be body here. So these are the key tokens. Leveraging this intuition, we can have a very simple way to extract that from unsupervised, corpus. That is just to do something similar to a causal intervention by dropping the long context in the natural data. Say that we truncate the part that have the sentence styronism and have a dog named body, and we use the same model to predict the same sentence under a shorter context. And you can see that most of the tokens, as we said, is still because they don't really require long context. They have a similar probability under this short context as well. But the word body actually have a dramatic decrease in its likelihood, because the model will never know the dog's name should be body. It's impossible to figure out without the context. So that means that we can actually use this contrast between the likelihood under the long and short context as a measure of how much this token require information from long context, or how relevant is this token to the long context. We call the log probability again, is basically the relevance score for each token about the long context. And we also try to use this metric to our previous, proof ID experiments on how this measure can predict the answer token correctly. And it's pretty good, by selecting a good threshold on the RXI, it can identify the K tokens with like a 85% accuracy on this long eval benchmark. I think it's pretty good. But if you are not even satisfied that, okay, what about the remaining like 14.4%? We can also try to figure it out, but you can zoom out a while if you don't really care about it, because this are minor points that we still found that some non-answer tokens still have a pretty large log probability gain. Like they are not really K tokens, but they still have a large probability gain. Why is that? So our intuition is that maybe if some tokens are very hard, just very hard to predict, either under the short context or the low context, or this context just don't provide enough information to predict that context, then you will have a pretty low, uh, sorry, you will have a pretty low probability under both low and short context, and under log transformation, maybe this difference will also be very large, but it just don't really mean that this token is very important. So what we do that we also take a look at just the simple log probability value of each token. That's just the px under li, and you can find that most of this token actually they have a very low log probability value, meaning that they are just hard to predict also under the long context. So if you combine these two metrics, try to filter out the tokens who have both high likelihood ratio and also a relatively high log probability value. It's not very hard. Then it's actually give you even higher accuracy on predicting the K tokens from the long EVA benchmark, like like a 98%. I think everybody should be satisfied with this kind of accuracy. So now, with this pretty good metric, we can actually have a new version of long context perplexity. Yep. So I think we know the typical perplexity measure is just calculating average uniform over all the tokens in the corpus. And the only thing that we have changed in long context perplexity is just to calculate the perplexity on the filtered K tokens induced by the previous metrics that we just discussed about. They only have two measures. One is the I think the log probability gain, and the other is the log probability value. We maybe have some different notation in the new version. Yeah, and that's it. So with this new metric,
There
yeah.
are two questions in the chat.
Oh,
Yeah,
sure. You can try to
yeah,
answer them first.
yeah.
Um,
Yeah.
actually, can you read the question first so other audience can know what the question is?
Sure. So I think Jeff have a question. Does a K token necessarily need to appear in the answer, or it's just the need to produce a log probability gain in the answer? So I think the thing here we are trying to do is that we try to select the tokens, the K tokens in the context. So the K token is not something, very important in the context. I think that's something I think we received a lot of, confusions from the readers that the K token is not the K tokens in the context, like this token must be attached to this token. But we think that is a K token only mean that this token in order to predict it, require it to, to be from the context. From a natural corpus, I would say that it not always, there's no, instruction following format even. So there's just some natural corpus, very long. There's no clear what is the prompt, what is the answer. Like still select the token that actually depend on a lot on its long context. So I don't know whether that answers your problem, but you don't have to get that from the answer if it's not a instruction following kind of data. So Ashley have a question, like, do you try causal intervention where the only corpus section containing the relevant K is removed from the context while keeping the rest of the long context? That is a good point, but I think the many we don't the short context we don't try it because I don't know whether you're asking this for the, synthetic data like benchmarks. Maybe we could do that, but for natural data, they are typically not simple, just retrieval tasks. The tokens that are important for, for this token's prediction might not be the same token in the context. So sometimes then it would be hard to identify what is the actually, that section from that. I guess you could utilize some, surrogate metrics like the attention scores distribution or something to figure that out. But I think that will be interesting to look into. But we just, I think we didn't do that yet. Okay. Sure. So if there's no more question, I'll move forward to the, yep.
Just a question on the key token thing. So when you say that you identify key tokens in a long natural corpus, so you go through the entire corpus, let's say token by token, and you consider everything that's before that token as the context. So you remove, let's say if you are at the third sentence, so you would take everything before that third sentence as long context. Is that so when you're trying to identify key tokens?
Oh yeah, I should be more clear on this. So we have this contrast of predict the same token under X, long context and short context. So in practice, by short context, we mean the context that models use to do pre-training. Like either you do that on 4K tokens or 8K tokens.
Okay.
That is short context. And the long context is the context length used for post-training, that like 16K tokens or something. Yeah. Because still have to fit into the GPU in order to calculate some prediction on that. Yeah.
Got it. Thank you.
Yeah, thanks. So yeah, let's move to the experiments that what we can really get from, just calculating perplexity on a few tokens. I think the very beautiful thing that we can actually, recover the correlation on every benchmarks that we have tested, like a long bench, long EVA, ruler. The correlation goes from 0.2 to 0.8. And the p-value is very small, so meaning that actually a pretty strong correlation, and it is all tested on the long perplexity is tested on natural data. And actually have a good correlation with what you tested on the synthetic data. Basically mean that if you really trust this metric, you can get rid of all this synthetic benchmarks, like human design ones. And we also found that because actually you need to use a model, right, to select what is the key token. That is one thing. It depends on the model, but also find it's pretty insensitive to the choice of this evaluator model. If you just need a, I think a basic model like a Llama 3.1, like 8 billion models, actually the correlation is very strong as well. So I think that's a good thing on using this model. You don't need to spend a lot of compute. And if you use our repo, we already computed what is the key token for you. So you don't actually need to load another evaluator model for that. And then if that really works, compared to the benchmark evils like a ruler and the other metrics, LongPPL is like really unique because it still rely on the perplexity, so it can just work on your own data. If you work with math data, coding data, you can actually figure out what is the key tokens for your own task using this metric. Now, have to define some, domain specific benchmarks for yourself. I think that's really time consuming, but now you can have a real world efficient and adaptive estimate of the long-term performance on the fly. You can also use that to monitor that during your post-training or even pre-training thing. I think that's something promised by us. And now we have also integrated that into like a pipe. You can just do pipe install LongPPL to just evaluate that. We're also working on, as suggested by Sony, to integrate that into the LM harmless eval. I think we probably can just have an easier way to evaluate that in the future. So that is about evaluation, right? So, and so this our result. You probably don't want to trust all our result, but I think we're also seeing some other people are still also try to report long PPL metrics. And for example, this is another like a paper tried to do long context understanding stuff, and they report both long PPL and PPL here. You can find that basically, if you have something new, then perplexity, because do average over all the tokens, don't give you so much gains on your own task. But if you actually test your method using the long perplexity, you might observe a larger gains of your own method. I think you can also think of it as the perplexity on the hard tokens that I try to optimize for in post-training tasks. So I think that's all about evaluation, but we also have, I think, have a better evaluation, meaning that we can actually mitigate the gap between the training and evaluation. So the more interesting thing would be that whether we can also leverage this for training as well. So we have a very easy adaptation, of the cross entropy loss to the long context cross entropy loss. That's just emphasizing the K tokens. But here, instead of just compute loss on the K tokens, we actually use a soft version of the reweighting terms. First of all, we just use the likelihood ratio, and we actually what was the word? Clip that to a certain threshold like gamma in order to avoid numerical issues here. And the reason why we use a soft reweighting with this likelihood ratio is that you don't want your reward to be too sparse for training, right? Because you actually want the model to receive gradients from everywhere, but not just the K tokens. And for this metric, if your K tokens, if your token is not K token, then basically it means that this token will have similar probability likelihood under both long and short context. Then this ratio that we use to reweight every token is close to 1. Then it's still pretty okay. You don't omit the non-key token. It's still training on it, but not to that much effort. I think another interesting to look into this long question is that we also get rid of the evaluated model. Previously, we need another model to compute what is the K token, and then I used to use that to evaluate my own model. There's 2 models there, but here we just use 1 model to compute both the likelihood, importance, and then use also for training models. Actually, we can observe the model actually become better and better through this process, both on estimate and on the prediction. Actually, it suggests that maybe long evil can be understood as a expectation maximization process, where the E step is just to do the contrastive estimate of token's importance, because that's kind of the latent variable to this problem. We don't really know which token is the K token. We just use that as a surrogate metric to predict that. Then you take the estimate and then you maximize your importance weighted prediction, and you get a better long contact performance. That get better long contact performance give you better contrastive estimate, and then you can bootstrap from there. Yep. And I think another thing to know is that it's still also very similar to our training, that you are just reweight every token based on rewards. The difference from RL that current RL people do that use sequence level or trajectory level reward. You basically put similar reward for every individual token. But here how we reweight each token is through a token level reward that you compute for every token based on their own relevance to the context. I think that's actually a more fine-grained way and potentially better way to do the process reward to some extent, but we don't need to rule out because it's about understanding, not about reasoning to some results. And the good thing is that so I think don't need for external rewards that we need to set up certain environment to have that, and then it's more efficient than RL because we don't need online sampling of the long trajectory or something. Okay, I see there's another question. Do we need to set the floor to? Well, that's a good question. We didn't really do it. We didn't really try it, but I think it just works well if you don't set the floor. I think the reason could be that if you look into the plot that we have before, I can maybe go back to that very quickly. there's a distribution of the tokens under this metric, then you can see that there are only very few key token that actually have, likelihood below 1. So most of the tokens are correctly upweighted. But yeah, I think it works without that. Maybe just take a little bit can get it better. Yeah, I think I'm pretty open to that choice. And the second choice for iSoft, do we have to detach it from the autograd graph? Yes, we have tried both, and yeah, detach gives us much better performance. So my own understanding is that it's also justify this RO perspective, because when we're doing RO, we still don't have the gradient from the rewards as well. Maybe that leads to some cheating problems. So you can still just use that for computer token importance and use that for reweighting the the train objective. Yeah. Okay.
Quick question on
Yep.
computational efficiency. So basically, when you're using LongCE, you need an extra forward pass to get the token probabilities,
Yep.
right? But on the other hand, it's sort of more efficient than RL. And sort of, I'm just kind of wondering how you think about the trade-off between sort of the gain in performance and the computation.
Yeah, that's a very good point. That's also our concern too, because you basically the evaluate step, you need the second pass basically to get some estimates. The good news is that the second pass could be more efficient than the first pass because it's a pass on the short context. So I think in total the computation like cost is 1.5x over the original cross-training training. So we have a comparison on the work clock time in our paper, showing that if you just still compare on the work clock time, this metric still give you much better performance. Meaning that it's worth the effort to compute the importance to prepare for your training, that you just train more and more data. Because I think for long content learning, the problem is that the signal is too sparse. That the really important token you try to improve is too sparse. Actually, you need that to improve your training efficiency. Okay, so that's all the basic performance. I'll just give 2 examples of them. That's over the training step. But if you look into the the work clock time is still pretty similar plus. Because it's just 1.5, it's still there. The gap is still pretty large that can improve the benchmark scores along either long eval or ruler by a significant margin, like 20% or 11%. I think typically a 5% will be recognized, significant on this benchmark, but I think this improvement is pretty significant. And we also evaluate the other on different LMs, such as the Mistral, Llama 2, Llama 13 billion models. We didn't go to even larger models, but I'm happy to see more results. We didn't observe some, scalability issues. So the improvement is pretty steady and, consistent across all model skills. I think that some good news is that LongCE cross-training is also started to be adopted in the recent work. This is a screenshot from a recent RWKV paper that came out that tried to combine some hybrid models, and they observed that if you train with long cross entropy, it's very important for efficient model like RWKV or RN to perform very well. Like on their task, they mentioned that if you just train with cross entropy, then the models will become pretty bad if you go to like S neither haystack 2 or as neither haystack 3. I think there are some benchmarks on probably ruler, also using ruler. But if you use LongCE that focus on the key token lag, actually give you 30% improvements on this measure. I think it's even more significant than our own experiments. I think that's also pretty promising. I think the reason could be that for efficient transformers, you have a very comparably to transformer, you have a limited capability or memory to what to remember. And actually, it's more important to find what is the right training incentive for your own model. Compared to transformers. Transformer is more noise tolerant compared to this kind of efficient LMs. Okay, that's my 2 cents on this, but I'm happy to see more of this. So to conclude this part of the talk, I just want to yeah, there's another question here. What's the typical lens SI? I think it's like 4K, 4K. It's that people use for pre-training. Basically, you're contrasting what you want the model to do with what the model already has. So what the model already has is the 4K contextual prediction ability. I think,
Quick question, so.
yeah, sure.
Yeah, so to compute the perplexity of PXI given the
Yep.
short context length, for example, K, you said like maybe 4,000, right? So it means like for a new token, you need to do like a sliding window. So how could you compute this kind of perplexity like for a new token?
Yeah, that's a very good question. And if you do sliding window, that basically every token we're gonna have a very different new context window. So basically making this model hardly unparallelizable. So what we do that we still need some approximation that if we let's say have a 16K token, we trunk that into like 4 trunks, and we compute that, and we just take every trunk as a separate data, and we use that to compute the likelihood on the short context. So you basically have more data, and then do more forward pass, but you can do that in parallel under the short context window. So that's our approximation to compute the PXI under SI. But I think it could be interesting to explore further, sliding window or other stuff to further accelerate it. I think there's much potential to do this.
So if
Yep.
you split the sequence into multiple segments,
Yep.
then at the beginning of each segment, the token, there are no contexts, right?
Yeah, I agree. I think especially for the first few tokens, it's going to be large bias.
Okay, got it.
Yeah, I agree. Yeah, so I think that's not perfect. But I think basically after I think a few tokens, like 20 or 30 tokens, the probably is also going to be okayish. But I think you're right. It's probably there are better ways to do this. But I think the problem is that if you just use sliding window in the transformer, it's not exactly the same as what we try to have, because through the sliding window model can have larger context just by propagating.
Yes.
Yeah. So that's
Yes.
why we did
Thank
this
you.
trick. Yep.
Mhm.
Okay. I'll go to the last 2 cents of this. I think the lesson I learned from this is that although we mainly discussed about the long context understanding problem, I think the methodology is pretty generic. It can work for things beyond long context understanding. So I think the whole reason we came up with this method is that we realized the nectar prediction is biased because tokens are not even generated equally. When we think of something is just easier to output than the other tokens. But that part is not accounted for during our training. So that's a big problem. So reweighting is, I think, a simple technique, just to let the model know you should spend more efforts on figure out this token. But there are definitely other techniques like chainsaw to solve every token or something. But I think reweighting is a good thing if you care about nectar prediction during pre-training or post-training directly. So I think the general way out to improve the signal noise ratio are challenging tasks, because on many challenging tasks like massive reasoning or other problems, there are actually only few tokens or like the certain patterns we really care about, and I think the good news that we have a sort of general methodology to identify the task-specific tokens. Here we use the likelihood ratio under long and short context, but essentially it's more generic than that. It's basically about the denominator is about the target model. So what we really want the model to achieve, the ideal performance of this, what's the real thing you want to do with this token. And then you contrast that with what you already have in the base model, already the performance. This contrast give you what value this token could add to your own task. So I think that's a generic idea of this work is can, extrapolate beyond just long context scenarios. For example, in knowledge distillation, if you look into its objective, it essentially also a importance related likelihood, next token prediction. And in their place, this is the teacher's probability, and this is a student's probability. You are relating nectar prediction with this knowledge from the teacher of what is the K token you should focus on. So I think that in that perspective, it's a unified view of what we have do so far. Okay. So with that, if there's no more question about this work, I'll move to the second work. I will move to be faster because that's already 45 minutes. Yep.
Yeah, our time is very flexible. You can
Okay.
talk what level you want.
Okay. Okay. Thanks.
I name it actually.
Yeah. So I think there's there's another question in the chat that's whether training with LongCE can lead to a degradation of performance on short context. That's a very good question. I think the methodological answer is that I previously mentioned that if you train on long context, still you have some weights on the non-K tokens, so you don't actually discard that. But result-wise, we also test that on the short context. We also test that on whether model reasoning ability, other ability degrades as we training that on long context. The result is that it's pretty comparable. It's sometimes better, sometimes little worse, but basically on the same level. So don't really, sacrifice the performance on the other tasks. I think that's also good news. It could be because actually we use sparse training signal that model kind of less overfit to this task. But yeah, that's it, just a speculation. Okay. All right, so let's move to the second part. That's about the transformers. Maybe there are more interest about that here. So I think we know a very big problem of LLMs or transformer in general is that they're oversensitive to the context, especially if the context is very long. It's very sensitive to the prompts. It's very sensitive to the ordering of the in-context samples. It's very sensitive to the similarly to needle position there in the haystack. So that actually leads to various we call position bias phenomena in the literature. For example, the attention sink. People observe that when you train a transformer, most of the attention actually goes to the first token in the attention map or something. And another is that loss in the middle. That if you do some basically similar to in-context learning, you put the few key in the query in the context, and you try to move the the desirable K query through the different positions in the context. If you can there's the significant shift of the performance at different positions, right? The difference can be as large as 20%. I think that's pretty large, and it makes no sense because this should be the same because there's no position information between different different query K pairs. Okay, and the challenge to this is that we don't really know how it happens, right? We know that have the bias, maybe have some intuition, but it's not that clear how it really happens. For example, what is the essential cause of this? Is this position bias even a good thing or bad thing or a natural thing? Or it's just limited to transformer, or it's also happened to everywhere, like a data introduced or something. But if we could really understand that, actually we could have something very good. Like we can have a guideline or how to design the transformer variant that don't have this kind of position bias. We can also have maybe a guideline on designing what is the right position encoding to get rid of this bias as well. But I think the obstacles to understanding that there are so many mixing effects of different factors in the in the LLM's behavior. Like it could be some position bias from the data, like my data is, or many people say that it's because my data is only activated in the beginning and in the end. The useful information are in the two parts of the context. So my model just learned that it's not the problem my transformer. Or there are models definitely. There are also position codings. Position coding also influence the position bias, but what is the contribution of each individual parts? We don't really know that. So I think in this paper, we try to have a kind of scientific understanding of this. So the first step is definitely just do a control experiment on ablating each part of that. So what we do is that we generate an independent key and query pairs for the data. So you just ensemble that randomly. So there's definitely no position bias in your data. And for position encodings, we tried 3 different kinds of position encodings, like no position encoding, which is the pure position bias from the causal mask or from the transformer. Then they have the decay mask alibi. I also have the rope, is more popular these days. Yeah, that's a question. Oh, I have to say these are 2 independent work. That from question from Jeff that does your work have any implication for position encoding? For example, when you're using LongCE, should you change the way you do position encoding? In the former work, we didn't do any of this. It's also like ablation study. We just change the objective and it works pretty well. I think most of the model we work with use rope position encoding. But here, as we said, 2 different. We only focus on the influence of the architecture, so we didn't change the nectar prediction. But I think it would be good to look into it. My speculation would be they are still pretty orthogonal in terms of their influence, because the long context selection of the tokens might not be that biased to certain positions. Yeah, but that's just the speculation. So here are the results of our control experiments. How to understand that is that we try to say if we put the ground truth token in the first token or the middle token, to say whether my prediction will actually is better if I put the if my ground truth actually in the first token instead of the middle token. You can actually see that if you have no position encoding at all, although people try to promise that it can mimic any kind of position encoding, but actually it's not. It's definitely have a certain position bias in the no PE as well. That always is actually the first is preferable to the middle. It's also preferable to the last, and there's basically not much difference between the middle and last. That's, I think, the first message. I think the second message is that if you use look into the deeper layers of the transformer, this bias also gets amplified. So deeper layers or deeper models, they will have deeper position bias. So models are biased with or without position encoding. And second of all, deeper model is more biased. And attention sink is more evident than recency bias. Like the first token is always more preferable than the last tokens. That is what we observed here. Also under this different position coding, still first is preferable than the last. So here's the question. So why position coding emerged even without data bias, even without position codings? I think there's definitely some inherent bias in the architecture. There's what does the modeling is? There's a question from Marcus, like, does the modeling the experiments includes residual connections? Yes, it's a GPT-2 architecture. Here we use the basically nano GPT repo for doing these experiments. Yes. Yeah, I think that's good. Maybe we can come back to that later. So if we take a look at the architecture of transformers, basically there are 2 different modules, right? The self-attention module and the MLP module. You can observe that there's only one module, which is the self-attention module, that actually makes the token together. The other just process the tokens independently. So this only possibility that position encodings can occur is because there is attention. So what is the attention's effect on the position encoding? It turns out we can understand that from a graph theoretical perspective. So many people try to argue that transformer is essentially a graph transformer, because you can treat every node as every token as a node. Then transformer just learn a adaptive graph every layer to connect this node and to do message passing over this dynamically changing graph. I also give a pretty good, perspective on understanding what graph, transformer is actually doing. For example, when I do this autographic prediction from how are you doing today? Essentially my causal mask is like this, right? It's a tensor few tokens in the previous context. And we can actually derive a corresponding computation graph. It's going to be a directed graph over all these tokens. And there are a few things I can actually observe from this graph. The first thing is that the first token is actually a central node. It's a graph theoretical notion that meaning that this token can reach to every other nodes in this graph. So it's like the centralized node is the source of all the other nodes. The second thing is that this is a very imbalanced graph because the first node can connect to all the other nodes, and then the connectivity or the node degree will decrease dramatically, I think, as the sequence continues. Like for this talking only have one output edges, right? So it's a pretty imbalanced graph, I'd say. So, and you can imagine that because this graph is already like this, and then when you're doing next term prediction, you're basically multiplying the attentions over and over, then this imbalance is gonna multiply through these deeper layers. So that's our intuition on why this could actually induce a certain bias toward the beginning of the sentence, because they just get more overall weight in the transformer during the propagation. So that's the intuition. But how to we can actually formulate that mathematically? So let's just focus on multi-layer attention. Let's assume the attention is just you have tokens and you calculate some attention matrices. It definitely varies according to different layers, but it's just multiply that through the layers. Here we don't consider residual connection, but even if you consider residual connection, there are some parts in the residual connected one have this larger bias, right? So, and if you compute the output of this multi-layer attention, then you can see that you can actually take all the attention matrices together as a new attention matrices. That's the accumulated effects of my token, prediction process. They're basically we can write it as a context selector because this is still something like a probability, and its prediction is like how for the ice token for the output token, the ice output token, how would that token depend on the G's token in the context? So you can see that ultimately the attention is doing a context selector operator that selects what is the important token from the context and aggregate that with a certain probability that is computed from the aggregation over other layers. And that's it. So any questions on this formulation? This is a formulation from previous papers, by the way. Yeah. Okay, so yeah, this probably is the overall contribution of every token to the final prediction. So we can actually just analyze what is the behavior of this probability to say, which token is just emphasized or have a certain bias. This would be the metric of our interest. So, and we can actually derive the attention sink following our previous intuition under this formulation, that if your layers go to infinity, like goes to deeper and deeper layers, then the probability of the first token, for every token attending to the first token, is gonna go to probability 1, meaning that every token, in the future, it's gonna, use almost every information from the first token. But that's gonna happen in practice because we don't only use a finite, finite layers. But that's give you the intuition, like if you just make the model deeper, that's gonna happen in the end. And for the other token, you can derive this, layer-wise, bounce on the context selector probability that will diminish like exponentially as you have deeper and deeper layers. And that's why we have the attention sink, right? We observe that not only in the attention pattern, but also, as we said, in the final performance, our model always try to prefer the first token over the last token because this transformer design on the causal mask is biased so much into the first token. I think there's something to be fixed. And this analysis is also more generic. It only works for sliding window and prefix transformers. Like sliding window, that I have a slice of the context that I only attend to, and that actually will slow down your position bias. That it could be imagined. Then prefix transformer that I have a bidirectional transformer to some of my previous context. Then you still have this for for the rest of the tokens, because all this prefix token are gonna be the attention sink. Not only the first token, but all these prefix tokens will have this shared probability, like a convergence thing. So, so let's finally get back to the influence of position encodings. I think many design of the attention position encoding are try to get. I think implicitly they actually try to get rid of this problem by the pure attention mask by introducing some bias to the recency, to the recent tokens. We call that recency bias. Like alibi, what they do is that they add some, decay mask to the original, attention scores. Then it's essentially try to rewire the graph so that later tokens also have more weights under this. But you can also imagine that if you just do this recency bias, you're just pulling up the probability of the later token, then there'll be something in the middle that's also overlooked. That actually is exactly what happens in the loss in the middle. So here we have some layer-wise influence of the position encoding. We can bound the positions, the attention scores after the position encoding according to their relative distance to the current token. Like here is xij, then it will depend on whether I and j are close, because it already enforced a exponentially decaying effect into the position encoding. And what we observed that for loop, I also have some results for loop. You can actually observe that they have different ratios to the alibi, right? It's like a exponential, like a squared, but because the theta, like the base for the loop is really much smaller. It's like very, very small. Then this is still something smaller than 1 in most cases. Then meaning that the loop actually will have a significantly smaller decaying effect than the directly have some decay mask like alibi. That could potentially explain why people try to still work with loop, because that it actually give you more information about the long context instead of just discarding that with a decay mask. So, and we combine the effects from the causal mask and the position encodings and analyze that through deeper layers. We will actually have this result. It doesn't look that good because it's gonna be a combinatorial number here, because that actually varies according to the distance between I and j and some other facts like the layers and the decaying effects. And also have some similar results for loop. But more like intuitive understanding is that I can derive what is the peak of my attention relative to my current position. So here is the plot to that. So the x-axis is about the distance between the token, the predicted token and the context token that is, the context token. this policy that actually if you when the distance goes from small to large, actually the overall attention score, like the P, is gonna firstly go up and then go down. Meaning that it's not actually the most relevant, most recent token gets the most, attention. It's like the tokens from a few tokens away get the most of the attention. Then if you go even longer in the context, you're gonna also get much smaller attention to that. And again, it will depend on a few factors. If your decaying factor is larger, then this peak will happen much sooner. And if you go to deeper, and this also I think goes later, because deeper models they have more attention bias derived by just the causal mass. So that's a larger content effect that so actually it's gonna delay that. So I think some practical takeaway that when you increase the decay stress M or the base rotation angle in the rope, can amplify the long contact effect and cause the model to focus on the more recent nearby tokens. Okay, and that's the thing that we derived. We derived a bunch of empirical observations about positional bias, like what's the position bias of nope, even without is there arbitrary position coding, or is there some certain position coding that actually mimic. Then also the relative PE and the interplay between the causal mask and the relative PE, attention sink, loss in the middle. And it actually turns out all these phenomena can be understood unifiedly through this graph theoretical perspective. I think that's what we found is pretty interesting. So a few takeaways that position coding is essentially caused by the graph structure of the tension, and NOP has its own position bias, and PE can make models more sensitive to the data bias. I didn't go to that, but yeah, I can also check it. If you, I think there's some result that we have. I don't want to go back into it, but we have some result that show that if you have any PE, like either alibi or rope into the models, if your data has some bias, we do have the experiment that you do have the data bias, then this PE can amplify the data bias, which is not that good. And relatively speaking, the nope don't actually amplify the data bias. I think we don't, because most of the theoretical paper, we don't actually go that far as the previous paper, try to fix this problem. But I hope that I'll give you a good understanding of what could be the path or to fix the problem, because it's essentially about balancing the graph propagation and through in the transform network. And we should expect that something that the probability of P should be similar to a uniform distribution. And we have a really good thing. And I think hopefully we have some other variables that can fix that. Okay. So, and that's complete the second part of this talk. So I think some final thoughts about this whole LMs and next prediction and transformer, that I think the previous, like the pre-training phase in the last 2 or 3 years might suggest that next prediction combined with transformer is a good combination for curve fitting. Let's see, it's very good to fit the probability. But the problem is that we want something more than just the distribution matching, just matching the the internet data. We actually, in order to get better intelligence, we want something more than that, because we want the capability, we want the robustness that's not really encoded in the next prediction task. That actually requires to redistribute the token or sequence reward for more efficient training to get most from the data, and also devise your architecture to improve your architecture to some extent, because that robustness might be important for your downstream tasks. Like for your coding, don't want your model to forget if that just longer in the context. I think the last point is that although I'm not from the LP community. I still found LMs very fascinating because it's not because it's LP, but because it's actually a more generic framework for us to understand how to do unsupervised learning or self-supervised learning. I think the most breakthrough of LMs is like actually introduce the context to the model. The LMs can predict or adapt the reputation or prediction to the context. So what the things that we have developed so far, like the LongCE or something, is actually how we can actually guess something from the context, how we can actually focus right to the right context. So I think these methodologies are universal, or that's a generic, can work for different modalities. They even work for different problems because all these problems are just creating different contexts for us to predict. Yeah, with that, I conclude my talk. Thanks.
Yeah, thank you for your amazing talk, and we can take several questions. So Marcos, I see you show up your hand, and you can feel free to ask any questions.
Thanks, Oli. Thanks, Yifei, for the great talk. It's a really nice work. I just have some questions. So the first one is, I'm kind of intrigued about the residual connections. I think that if you remove them, it creates this huge oversimplification for transformers, right? And I'm not sure if like the results would hold, the theoretical results would hold with residual connections. Like for instance, I tried like some simple tasks with Nope, right? And indeed, like if we remove the residual connections, yeah, we have this bias towards first tokens. But if we include the residual connections, we can actually learn these relative position encodings as suggested in the original Nope paper. So that's one question that I have for you. Like, what do you think about the residual connection parts? Like, would the results hold with residual connections or not?
I think in our analysis, actually, we also analyze the case without the position encodings, right? So this formulation is without position encoding. All this derivation is for at least a branch without residual connections. And our like message is that if you don't have position encodings, this position bias is gonna be more significant because it's just multiplying more and more attention matrices, causing significant, heavier biases. Yeah, and if you have the residual branches, you basically have an ensemble of models from different depths. Actually, I think could elevate the problems to some extent. Yeah, that's my understanding, but we don't really do the experiment, but I think it was worth looking into. Yep.
I see. That's very interesting. Another question that I have. Sorry for hijacking all the questions. Another question that I have is regarding sparsity. Like, do you think that if we do some kind of sparse graph, this would change dramatically the results?
Oh, that's a very good question. So I think definitely, and it can be understood under this framework because, as we said, the things is the important thing about you should make this graph like less biased or less imbalanced. I think if you make I think I won't say that you just making it sparse will definitely make it more imbalanced. Less balanced. Yeah, the reason is that you can still design very imbalanced graph, even just connect to a few tokens. That's possible, but I think in general, if you use sparsity, that actually you eliminate a lot of the connections in this, and then I think actually will in practice will help get rid of at least alleviate the position bias by a significant margin. So that's also our intuition behind the sliding window. If you use sliding window, you are essentially doing a sparse attention just over the recent few tokens. Then actually you can prove that it actually slow down this position bias by a certain coefficient. Yeah.
Thanks. That makes a lot of sense.
Yep. Thanks.
Okay, Shish, can you open the mic and ask a question?
Yes, sure. Yeah, really great talk. I got to learn a lot. My question is on this position bias. What are your thoughts on like mask discrete diffusion models, like the text diffusion models, where you can attend to it's bidirectional and it's not a fixed prefix, but you attend to the entire sequence at the entire same time and you're denoising.
Mhm.
Is I would assume that it would have some it alleviate some of this problem, but how far does it go, and what are your thoughts on that?
Yeah, definitely. I think that's very good point because we observed in both of these experiments, and also I was to accurate that the tension sink or the causal mask is the most important source of position bias in transformers. So it's all caused by the orthographic structure. If you don't have that, as in bidirectional transformers, as used in diffusion models, then you don't have this large source of position bias. I think that will help a lot. I think that's part of the premises of diffusion transformer or diffusion language model in this space. But I think another problem is that then how you can actually encode your position information better. I think rope. I don't know whether rope is a good choice because it's also designed just for language models. It definitely can work. I think REP can work, but it's also we can maybe have a more tailored one to the bidirectional one, and this understanding or framework could be a good guideline for that. I don't have a clear thought on that now. Yeah, that would be something cool
Thank
to
you.
work on. Yeah.
Thank you.
Thank you.
For the next question, so Corbinian,
Yeah, thanks for the two nice talks actually. Regarding this graph problem, I've been working a bit on that in the past. So it's ultimately, I think it boils down to the problem that you have many paths from your first token to the last token, but only like a single path in your graph from the like previous token to the last token. So I'm not sure if sparsity can really help there, because I mean it would just cut off a few connections maybe, but ultimately you would need to like reweight everything to make it like you would have to somehow enforce that makes things stable, right? Or what's your deeper intuition about this, like perception of having this as a graph?
Yeah, I agree. I think transformers are graphs. I 100% on that. I think the challenge, I think the difference is that definitely it's a dynamical graph, how you can deal with that. And about the point or sparsity, I think the problem is with softmax. Like when you do softmax, you actually, even if your models are not, generating, not really try to focus on certain paths, but doing softmax will actually get you some non-trivial distribution on each of the tokens, especially if your context pretty long. Then kind of dilute the information to some extent that actually is going to be good if you just cut the information with sparse attention. That's, I think it will, in this sense, will get the model to have less position bias because the model just less connected to the later tokens is less, unnecessary position bias there. Yeah, that's my intuition. Right, but I think there are other problems that you can also fix that within the softmax attention paradigm that you can use. People use I think some I forget the word, like you can fix the softmax attention. You focus less on the irrelevant tokens by dividing softmax or something. It also works. Yeah, I think it's a kind of unified framework to understand all these techniques that we have developed so far.
Yeah, I guess like the softmax is pretty good in that it's it's already normalized along the sequence dimension, right? But in the depth dimension, because of the residual connections, you don't have any normalization. So every additional depth layer can basically add up to each other. And I think that's the main problem. But yeah, thanks for the nice intuitions.
I agree. Yeah, I think adding residual connection is definitely much harder to analyze. You know that definitely you should know that in the literature, like there are some Google people trying to analyze it. Yeah, I think is when you have a residual connection is a combo. It's a combo of multi depths attention. Then I think still if you make some simplification, there's a way that you can just only extract the attention. Then it's gonna be like I plus A square, and then there in combination is still a new attention mechanism, right? And I would believe that it still have attention bias, right? But by adding over this, it should make it less severe. Yep.
I was thinking about sort of possible ways to mitigate position bias through sort of architectural pathways. Like, what do you think about sort of, I don't know, like given the findings on like, how causal masking is inducing early token bias and like attention sinks, like what about like an architectural module that would like upweight the key tokens that like what do you think about that?
Yeah, I think that's a good point. Because I think the attention is already upweighting the key tokens by doing attention. Right? It just don't have the positional information. It only do that thematically. I attend whatever information that's important, but overall, because this whole causal structure, marginal distribution is still biased. I think maybe we could try to fix that in the attention, not still fully driven by semantics, but driven also by its positional marginal distribution. And we can counterfeit that through architectural designs. Yeah, I think that could work. Yeah. Yep.
I think I have one very high level general question that do you think that if we consider training that position bias is a positive or negative effect, because that I think that it somehow stabilize the training process. Yeah.
First of all, why do you say that it stabilize the training process?
It just means that I just say that, for example, yeah, just I find that yeah, because that some papers that they propose that introduce some meta token at the beginning, yeah, or it seems that these tokens that make the training a little stable. I'm not very sure. Yeah.
Oh, I see. You mean basically the attention sync paper? They still put the attention sync there, and then
some further paper along this direction doing some exploration. Yeah.
Yeah, I agree. I think, but I think probably it's the reverse of the cause and effect. I think it's because the transformer already have this attention bias. Then you have to keep the attention sync in order to keep this bias. Otherwise, your model don't generalize. But it's not because ultimately this help generalization. Then I would definitely want to have this. I don't say it definitely have to be the case. Because you can still do bidirectional training on this data can still get very good performance. There's no position bias. I still think position bias, if your data is not position biased, as we do in this control experiment, then your model shouldn't be biased. There's no harm in learning invariance. Typically, it has theoretical results showing learning invariance can help. The models, because the data is, like, let's say it's invariant, and then if your model is also invariant, then this can couple together to get better learning efficiency. So that's my take on this. yeah, I think it's still better to design the one without the diffusion bias. Maybe diffusion language model is the way out to some extent, but maybe it can also have some way to fix that just inside the transformers. I think the problem is with transformer is that transformer use this very simple way to to enforce the autograph structure, but that's the position bias is just, as we said, the byproduct of that training goals. You can imagine that you can still use a bidirectional transformer to do nectar prediction, right? You just do that every time. It's inefficient, but that's gonna have no position bias. Yeah, how to bridge this to efficiently is the problem.
I see. Yeah, I think this makes sense. Yeah.
Yeah. Great. Thank you for the question.
Are there any questions?
Yeah. Can you hear me?
Yep.
Yes. I do remember a tweet from you. I mean, you mentioned it here as well, where you can sort of use the first paper, the method in the first paper, to improve on reasoning as well, to identify key tokens in reasoning as a alternative to PRMs. Do you have any more insights on that, or was that like a? I mean, I understand that it's a word direction worth exploring, but anything else that you can share?
Yeah,
Efficient.
I can share that definitely. I think I can go back to this slide. That's what they try to say here. That is this methodology should be general than just long context. So if you want to design something for reasoning, you could also think in this way that I have my base model ability, then I have this ideal performance. Maybe there is some model good at reasoning. Then I can use this contrast to do that. And how to do that without another model, and how do that bootstrapedly is that problem. Yeah, we are working on this. Hopefully we can see more of this in the upcoming months. Yeah.
Okay.
Okay. Maybe we can wrap up the talk here. And thank you, Yifei, again for this very amazing talk. Very thank you.
Thank you. Thank you all for coming. Have a nice day.
Thanks.
Yeah, have a nice time.
Bye.